Right, then let me show you the slides about the finite volume method. Again, these are more motivational slides about finite volume methods. And originally it was developed by McDonald in the 70s, 1971. He was interested in flow phenomena around the wings, or in this case, like turbines. And so the finite volume method is very popular in fluid dynamics, fluid dynamic problems. And you see here, I copied you the summary or the abstract of his paper that he published. And the main point that sticks out is in the second sentence. So he is focused on study transonic flow through two-dimensional gas turbine cascades, sufficiently predicted using time-dependent formulation of the equations of motion. And then comes the important part: an integral representation of the equations has been used in which subsonic and supersonic regions of the flow field receive identical treatment. And that's the main ingredient for the finite volume method. Finite volume method looks at integral representations of the equations. So far, we know about the strong form of the equations and the weak form of the equation. And here we're going to look at the integral representation of the equations. So where is it used now? Well, it's mostly used in, for example, computational fluid dynamics, because it's very well suited for transport problems where you have mass transport or other quantities that are transported in terms of convection schemes, etc. And so, for example, there is a package called SU2, which is a multi-physics package which uses, for example, the finite volume method for the computational fluid dynamics implementations. Then we have, for example, a package called ClawPack, where you also have a focus on geophysical problems. For example, you can simulate landslides, which is a transport problem of mass. So it's important to look at the conservation of mass and find a method which is able in dealing with that in an accurate way. And it's mostly famous for tsunami simulations, which like governed, for example, by the nonlinear shallow water equations. And then you can have these nonlinear phenomena, like, for example, shock waves. Again, these can be described by conservation laws, and then the finite volume method becomes a good method to look into such phenomena. And then, for example, heat, mass transport problems, for example. And ClawPack here at KAUST, we have, for example, David Catchison, who is quite an active contributor into one of these ClawPack packages, PyClaw, the Python version of it. So we actually do have really one of the experts here in-house at KAUST. Then also what I found interesting, for example, there are mainly two global numerical weather forecast systems in place. One is the model used at in the US at NOAA, which is the American model. And that one uses a dynamical core, which is based on the finite volume method. The other system that will be used is the ECMWF European Global Weather Forecast model, which is based in Reading in England. But so this one uses the finite volume method for global weather forecasts, for example. And then you have quite a bit of commercial packages which implement fluid mechanics or the computational fluid dynamics part with the finite volume method. So when you look at packages like ANSYS Fluent, for example, or SFX, that's based on a finite volume method approach in solving these flow problems. So it's quite popular actually in commercial packages to use that method. Sometimes it has been superseded by the finite element method, but the finite volume method still has its applications, and they're still widely popular and used, these packages. So when I try to put together a few of the more popular packages which use the finite volume method, we have, for example, the ANSYS packages, Fluent and CFX, which use the finite volume. There is also the Star CCM Plus package from Siemens that is mostly used, for example, in the automobile industry, looking at airflow around cars. And then there are quite a bit of open source packages. So ClawPack, you saw, is used quite a bit for geophysical problems as well. But then also OpenFOAM, SU2, PhyPy, CodeSaturn. These are all packages which use the finite volume method, maybe even together with the finite element method, etc. And then the book, when we come to geophysical problems, the most important one is probably the one from Randall Levesque about the finite volume methods for hyperbolic problems, which is the underlying book for the ClawPack package. So Randall was then developing the ClawPack package from this, based on this theory, basically. Then when I tried and look up some online material, for example, on YouTube, what I found quite well done are the YouTube videos you find from Aidan Wimshurst called Fluid Mechanics 101. And he explains very well the finite volume method as well. So I kind of liked his YouTube videos most, that I could find as an online tool. So I'll provide you these slides, and then you can look at these materials as well. Good, so it's a very popular method, not used that much for wave propagation, especially the linear wave propagation, but is mostly suited for actually nonlinear phenomena, where you look at conservation laws and then you implement the conservation laws with the finite volume method. Good, so let me go to the notes, and then we just start by, like we did for the other methods, by looking at these, a simple example, and then see how this would be done with a finite volume approach. Do you have questions on that so far? Good. So let's take a pen, piece of paper if you want, otherwise you will have these notes as well, which I will give you. So let me try and put up the whiteboard. Good. Do you all see the whiteboard? Right, okay. Good, so let me start just quickly putting down what this finite volume method is. Just a short sentence. So the finite volume method is based on the integral form of partial differential equations. And then it discretizes the physical domain into grid cells and approximates the integral values over each grid cell. So what we will end up is, again, a system of equations which we can put into a matrix form and then use a matrix solver in order to solve. That's going to be the goal. That's okay. But let's start with an example and look at the integral form. So let's start with the integral form. So the example that we start with is the same example that the example we used for the finite element method. Not sure if you still remember, but what we started with is the following. A 1D partial differential equation for a field U, which will be in a domain from 0 to 1. And the equation looks like that. We have here the second order derivative with respect to x of u plus f is equal to 0. Do you remember how we called this equation?
Steady state.
Say it again, Kali.
Steady state equations, diffusion.
Right, right. That's the steady state because there is no time dependence. Steady state diffusion equation. And the equation is also called Poisson's equation. It's quite a famous equation. How would that look in 3D? I put you the 1D equation. Do you see how it would look in 3D?
We can use the nabla
gradient.
Nabla operator.
So it would be the Laplacian, which we can write this way, for example, of u. Plus f equals 0. Now the Laplacian we could write as the divergence of the gradient of u. plus f equals 0. So this would be in 3D, for example. But let's define also the boundary condition. So we use the exact same example like we had for the finite element method when we started looking at that one. So we have a boundary condition at the right point. So u at 1 is equal to q. Who knows what boundary condition this is? Dirichlet or Newman?
Dirichlet.
This is Dirichlet, right? And then we had the derivative of u at point 0 was equal to, let's say, minus h constant. And this is Newman boundary. And for the fourth term, we just use some initial function f of x. So what is the integral form of that equation? Well, we just integrate over the domain. So the integral form is simply the PDE integrated over the domain omega, which goes from 0 to 1 in this case. You could also use 0 to L or something. It's just to use the same example like for the finite element. Right, so what do we have? Well, we just integrate over omega of our equation. And if you want, we can put this as two integrals, one where we have this diffusion term plus one where we have the force term. It's equal to 0. Good, that's the integral form of the equation. So how is that connected to the weak form, which we know from the finite element method, the spectral element method? What is the difference to the weak form?
In weak form, we have the test function.
The test function, right? So in principle, the weak form would use a test function w times this equation term, or the dot product basically with the test function if it's in 3D. So you see the weak form and the integral form are almost the same, and actually they are the same if we say w is going to be a constant which is equal to 1. So if we use a test function which is constant and 1, then the weak form is exactly the same like the integral form. So that's why sometimes you see that when they talk about the finite volume method, they speak about the weak form rather than the integral form. So sometimes they mention this is the weak form, or sometimes they mention this is the integral form. So it's basically a special case of the weak form when we just use the test function as being a constant to 1. But then they are the same. just to make the connection with weak form and integral form. But so the finite volume method looks at the integral form. Right.
Professor,
Yeah.
why in this equation they are both in a domain from 0 to 1, but for the left side it is integrated over dv, but right side is dx.
Oh, right. I could use dx as well. Sorry. Because I use omega here,
Yeah.
it's kind of more general. I just say, well, it could be a volume as well. But then you're right. Then this would then be this part. Then we could say this could be in 3D or whatever dimension you like. But you're right. Since we look just at the 1D problem, then this could be dx instead of dv.
Okay.
Yeah, sometimes I try and be, or I prefer sometimes the more general formulation with omega and dv, so that you can see it's kind of a general formulation, a general case. It doesn't need to be just applied on 1D problems. But right here, the equation is for 1D. Good, so now let me add a few points about the finite volume approach. How we want to going to solve this integral equation. The first thing I want to mention is Gauss theorem. So the finite volume method, it really came from finding solutions to conservation laws. That was the main motivation. And conservation laws, they often include a term which has the divergence of a quantity. So let me just quickly state that I'm motivated by conservation laws. Where often the divergence of a quantity is involved. We look at Gauss theorem. Which is fundamental for the finite volume method. So who remembers Gauss theorem? If we have an integral of the divergence of u integrated over the volume is equal to what? becomes a surface integral over the surface of the volume.
U time normal.
Right, the dot product of U with the normal at the surface. Now integrated over the surface. So here we have a divergence of U, which is equal, and here we basically have the flux of U across the surface. For omega. So that's a fundamental ingredient of the finite volume. Whenever we see a divergence of a quantity, we're going to apply Gauss theorem and use the flux of the quantity across the surface rather than the divergence expression. You remember, for example, for conservation of mass, how the equation looked like? We had this at the very beginning, and we looked at conservation of mass. What we had, for example, is the continuity equation. Which was that time variation
of
the
density. Yeah, and divergence of density and velocity.
Times the velocity field V was equal to 0. So now you see if we take the integral form, this plus this over omega, then this term here can be rewritten as a flux term. Here we look at the quantity rho V dotted with N over S. That's Gauss theorem. So the finite volume applies Gauss theorem to these divergence terms, integrals. So this would be conservation of mass, for example. Similar for linear momentum, we also have a divergence term. Similar for conservation of heat or energy, there's also a divergence term involved. So that's very much the motivation of the finite volume method. We see this divergence term, and then when we have it in integral form, we can use Gauss theorem. And rather compute it as a volume integral, we compute now these surface integrals. That's what we are interested in, which are these fluxes of the quantity across the surface. And further, it allows also that the field, the quantity doesn't have to be smooth. It can have jumps, discontinuities, for example. It's, for example, interesting when we look at shock waves. Shock waves are nonlinear phenomena. When we just look at the wave equation, we cannot really treat them. But if we look at the conservation of linear momentum, for example, and then using a finite volume approach, we could actually implement such phenomena. So that's very much a motivation for these finite volume approaches. Good. So Gauss theorem is a fundamental ingredient. The next part that we're going to look at is a distinction between a self-centered approach and a vertex-centered approach for the finite volume method. So if we look at a mesh, for example, at these cells how can I put that down? We could have something like that. And here maybe some other cells, etc. So a cell-centered approach looks at the midpoints of these faces, these cells. And the quantity, for example, U in our case, would be defined at these cell centers. So this is called a cell-centered approach. We could do the same thing, but using the endpoints of these cells, so the vertex points of these cells, and then trying to make you the same grid. But now we look at the vertices of these elements of these cells. And here now, the quantity will be defined on these vertices. This is called a vertex-centered approach. So we have these two options, and the meshes are often called dual, to go from one to the other. Now the approach that we'll do in this class is we go with a cell-centered approach, which is also a most popular approach when we come, for example, like packages like OpenFOAM, etc. They use cell-centered approaches. And I'll show you in a second what's the benefit of that, but there is no clear distinction which one is better or not. But so here, for our class, we choose a cell-centered. Sometimes it's also known as a centroid-based approach. So how is the centroid defined? Let us do that. So the centroid for a grid cell, call it omega E, is defined as the integral over that cell, x minus the centroid point, let's call it P, but this integral vanishes. Then P, the point at xp, is the centroid. And similar, we can do the same for faces. The centroid of, let's say, a face alpha. So let's say here we have a face alpha. And then a point x alpha, which is the centroid of that face, is given by now the surface integral x minus the centroid point integrated over this face, self face, will vanish. Then the point x alpha is the centroid of that face. This is clear so far? Right.
Professor?
Yeah?
The xp, x alpha here is just the points, right?
Right. Point locations, yeah.
And the xp is just a arbitrary point in a volume. The x alpha is the arbitrary point on the surface, right?
Right, yes.
Then,
But similarly, we can define like also for a line, for example. So if we have a line, then what would be the centroid of that line? Where it would be the integral over that line. Let's say from A to B of position x minus, how shall we call this point? Our centroid would be xc. Dx has to vanish. Which makes the centroid for a line is just this midpoint.
so x is our variable.
Right.
Okay, thanks, Professor.
Good. So for the discretization, now what we assume is that our field U within one of these grid cells can vary linearly. So to have at least second order accuracy, of our discretization, we assume that the field U, but also any other fields that we use in case, varies linearly within each cell. So that we can write that U of x will be U at the centroid position plus x minus xp difference times the gradient of U at the centroid position. Where UP is just U evaluated at this centroid position xp. So the field can have a gradient within each cell. Then it's a linear function within each cell. So from this, it follows that the mean value within the grid cell is represented by the variable value at the centroid P. What do I mean by that? Well, let's define the mean value over the grid cell. The mean value is defined as 1 over the volume of the grid cell integrated over it of that field values within that grid cell. So that would be the mean value, mean or average, whatever you prefer, average value over the grid. So if we have that linear function of u, then this is represented by u at the centroid position, which we can just write up, then this is exact. How do we see that this is second order accurate in case u would not be linear? Well, let's do that little example. So note if u is nonlinear, then this is at least second order accurate. How can we see that? Well, let's write the mean value. Now we can write out what our function u is. So we have the integral, and now u, if you look above, is up plus this x minus xp times the gradient of u evaluated at xp, plus now would be terms which are second order of u. D omega. Now let me try and move that a bit. dv. Then, well, let's write this out. We have this first term of up dv plus the second term of this linear variation plus then whatever comes with the truncation of u squared. Right, so up is just a scalar, so we can take this in front. Then we have 1 over VE times the integral. Just the volume. Second one, the gradient as well. For this gradient, just the scalar as well. And then we have 1 over VE of this integral of x minus xp dv plus this second order term, which we just write as second order term. But here you see this part is V, the volume. So the first term is just UP. And this part here, it vanishes because that's the definition of the centroid point. So then all we are left with is this second order term, etc. So this is second order accurate. If we just say the mean value is equal to the value at the centroid point, that's at least second order accurate. Good, let me move this a bit down. So that's one of the reasons why we choose these self-centered approach. Here we look at the values at the centroid, and it happens that this value is exactly the mean value if the function is piecewise linear. If u is piecewise linear, means linear within each grid cell, then the mean value is exactly the value at the centroid point. Or otherwise, if it's not linear, then at least this would be second order accurate. So again, just making clear that the mean value is equal to the centroid point value. This is exact for linear fields. Here. The same we can do for the faces. So the mean value for a face becomes just the value at the face centroid. Again, this is exact if the function is a linear function. Right. So something that, if you now look at Gauss' theorem, if you go back to our fundamental theorem for this method. So what's happening to Gauss' theorem if u is this piecewise linear function? let's write that down quickly. So, and this comes basically to the approach that was initially taken to solve the wave equation. So for a smooth enough field U, means that U is almost linear within each grid cell, then let's look at our divergence of U term. Well, if the divergence of U and U is almost linear, then we can just say, well, this is the divergence of U times the integral. Since diff U is then just a constant, we can take it out of the integral. And then this is just this divergent term times the volume times V. Right, but we know from Gauss theorem that this has to be equal to the integral over the surface of that grid cell of U times N. And so again, now for the integrals over the surface, you can just approximate them by the values at the centroids. So if we are in 3D, then we can just write that based from the divergence. Well, let's just write it that way, that the derivative for component I, x, y, or z, then becomes 1 over the volume times the sum over the surfaces, which we can call alpha. Let's think of having here xp, and then we have corresponding surfaces x alpha, for example. So it's the sum over each surface times the surface area S alpha times then the component Ni, the normal of that surface, times Ui evaluated at the centroid point x alpha. So this is the volume of the surface, of the grid. And here we have surface area for the surface alpha. Ni would be the normal. And Ui alpha would be the component I evaluated at x alpha, the centroid of that surface. So now we have an approximation to the derivative of u. The approximation is given by just the values at the centroid points of the faces. So if we want to know what the derivative here at point at the centroid P is, we can just take this sum over all the surface centroids and then have it approximated by that. In 2D, how would that look like? Well, the same, but now instead of the volume, we would have the surface area. And alpha would be now the sum over all the edges with length L alpha times again ui alpha. And if you want in 1D, let's just assume we have x, so the derivative would be 1 over L integrated for Ni alpha u alpha. And I would be x. So think of having a cell. The normal always points outwards. So we would have, let's say, N1 and 2 pointing outwards. The length of the grid cell would be L. And then the centroid point would be in the middle here. Which is really just another way of writing that we would have ux2 minus ux1 divided by L. Well, it's not alpha here, this would be the center point. The point alpha would be here. This is x2. Here we will have the value ux1. Right, so this approach was the first finite volume approach for wave propagation made by Dormi and Tarantula. And that was 95. So they approximate these derivatives based on this finite volume approach. And I just use these derivative approximations to solve the wave equation. 2D, okay. Good. But so one major problem we still face is we need to find these values at the faces, at the surface centroid positions, for example. So you remember what we have are the values given at the centroids of the cells. So somehow we have to find the values for the centroids of the faces. So somehow we have to interpolate then these values, given we know that what the values are at the centroid, the cells. And so this becomes now a problem of interpolation. How do we find these values at the faces? Similar here, for example, if you look at the formula, all these values here are evaluated at the face centroids, which we don't necessarily have. What we have are the values at the centroid points. So how do we interpolate? So let's call this phase interpolations. And so the question is, how do we find the surface integral values for the grid cell faces? Which translates with our cell-centered approach to how do we find the values at the surface centroid locations. And so here now the finite volume method can give us different interpolation schemes. And it's like when we chose the finite difference method, we have a bunch of finite difference schemes, forward differences, backward differences, centered differences. You can think of the same choice that we have with the finite volume schemes here, with these interpolation schemes. And so I give you like the three, let's say, most popular schemes. And the first scheme is called the upwinding scheme. So let's think of the problem of Gauss theorem, where we have now these surface integrals for value u ds, which, like above, we could approximate by these sums over the faces of the value at the cell centroids, at the face centroids u alpha. So let's look at the upwinding scheme. So we can think of having two cells. One cell where we have here the centroid XP, and then the neighboring cell where we call the centroid N, XN. And what we want to know is basically what the value is now at the phase between these two cells. So for XP, we find maybe a value UP, and let's say for XN, we have a value UN. It can be different. So the upwinding scheme either takes the value from UP for this centroid of the phase, or it takes the value of UN, the neighboring cell. This is mostly depending on in which direction the flux would move. Think of a transport scheme. You have a transport in a certain direction. So the flux, it moves the quantity in either to the left or to the right. And so our value at the centroid of the phase, U alpha, is then either the value at the centroid at grid cell P, if, let's say, the flux is positive, or it's the value at the neighboring cell if the flux is negative. So if the quantity moves to the left, then we take it from the neighboring cell. If the quantity moves to the right, then we take it from the our reference cell P. That would be an upwinding scheme.
Professor?
Yeah?
Is the UN here is also the centroid point?
Right, from the neighbor, so yes.
Okay. And what is meaning the flux is bigger than zero?
Right, so if we would have convection, for example, or convective schemes, then the convective flux we could write as being transported with the velocity v, rho v, of our quantity u, evaluated at the centroid, times n times s alpha. That would be the convective flux, and v here, this would be the transport velocity. So think we have a convection with a transport velocity v, which moves either to the left or to the right. So we can define what the flux would be this capital F here. If the flux is positive, it means it moves to the right. If the flux is negative, it means it moves to the left. So what is the positive advantage of the scheme? The upwinding scheme is stable, no matter what. The disadvantage of it, it's only first order scheme, and it smears out the solution. Good. let me give you two more schemes and then we finish for today. So the next scheme I want to give you is a linear upwinding scheme. We would have these cells again. And now we not only have the value P, but also a gradient. So we also have the gradient of U at that point. So again, this would be our centroid P and N. And now it means we can basically extrapolate what the value should be at the face. So U alpha here just depends on this distance to the centroid. And that's called the distance dp in this case. Or again, in the neighboring cell, this would be the distance dn. Here we might have a different gradient. And so in this case, the face value U alpha can either be UP plus this linear contribution from the gradient. Again, if the flux is positive, or we take it from the neighbor cell if the flux goes in the opposite direction. This scheme is called linear upwinding. So we need the gradient, the centroid, plus its value. What is the advantage? Well, this scheme is second order accurate. What is the disadvantage? Well, this can lead to artificial oscillations. Meaning that if we extrapolate to the face value, we might not be very accurate, and then it will start oscillating the solution. And so this led to more advanced and sophisticated schemes where we use limiter functions. So you can have also called limited linear upwinding schemes, which try and improve on these oscillations, for example. Right, and the third one is called just a linear scheme, or it's also called a central differencing scheme. And now again, we would have these two grid cells with P and N. And then we have maybe a value UP, then the neighbor a value UN. And so we can just interpolate to the value at the face alpha. And so in this case, U alpha, we can define it as this factor phi times the value of UP plus phi times the value of UN, where this phi is the ratio of the distance of the face point minus the centroid at P over the total distance between neighbor centroid and the centroid at P. So it's a linear interpolation between now the 2 points. And this factor just makes it more flexible. So if one grid cell is smaller than the other, etc., that we account more from the closer point. So it's a linear interpolation between these 2 points. What's the advantage? Well, this scheme is also second order accurate. The disadvantage, the same thing, can also lead to artificial oscillations. Good. So let's stop here. And then next Thursday, we will then use our 1D example and try and implement this. So the next step would be starting to discretize our initial equations, our integral form, this one here we had. So we start discretizing this over the grid cells and then set up the matrix form in order to solve it. Good. Do you have questions so far to the approach? Takes a bit of preparation, but the main ingredient is Gauss theorem. Something we always use in the finite volume method. And then think of these different schemes like in the finite difference approach, where we have different options, how we want to make these interpolations. Some have better accuracy, others are more stable, for example. Good so far? Everything clear? Good, we'll continue then next Thursday with that. Then I think, yeah, let's look at next Thursday then also at the little code example. How we would actually code this up with the finite volume approach. Good? Just theory today, yes. Again, the learning you have to do. I cannot teach you anything. No, good. Then we're all done for today. Already over time, right? But so we see each other next Thursday. Good with everyone?
Thank you, Professor.
Okay.
Thank you,
Good.
Professor.
Then
Thank
enjoy
you.
your day, enjoy your Sunday.
Bye.
Bye, everyone.
Bye.
Bye.